we've just been sort of introduced to the concept of polarity, which is the difference in electron density between one place in space and another place in space. That's all polarity means. And so we've sort of been looking at electronegativity. That concept was introduced a little while ago. And electronegativity just means one atom can pull on electrons, the electrons in a bond toward itself more than another atom in a bond. So something with a very high electronegativity, like fluorine or chlorine or oxygen, something like that, has a relatively large nucleus for the row that it's in and has a strong pull on electrons. Whereas other elements, mostly like metals and other elements like that, can't pull on electrons quite as tightly and either give them up completely and make an ionic bond, or form a covalent bond where they don't really have much of the electron cloud around themselves. And that leads to a polar bond where there's more electrons in space on one side than there is on the other. That will lead to a polar bond, but the question was, will it lead to a polar molecule? And then that's where we started talking about shapes. And we were introduced to this new fancy concept called VSEPR. And VSEPR, really all we need to know about VSEPR is that electrons are negatively charged and don't like to be around each other. And so when we're looking at putting a shape of a molecule together, basically all we're talking about is the atoms in that molecule will try and situate themselves as far away from each other as they possibly can, because atoms are surrounded by negatively charged electrons. The bonds themselves are made of negatively charged electrons, and some atoms have lone pairs of electrons that take up space, and they're going to repel electrons as well. So basically, every molecule is going to try and arrange itself into the most stable shape that it can, and that stable shape is reducing the ability of electrons to push against each other. So they'll try and reduce that repulsion by moving away from each other as much as they can. The other thing that we had to sort of consider when we're thinking about that is that single bonds, double bonds, triple bonds are really just a density of electrons in space. That's really all they are. Because you remember that when we talked about the sort of the quantum mechanical view of electrons, we weren't just talking about, you know, here's an electron in space and here's an electron in space, and you know, they're repelling each other. What we're really talking about is the density of where we can find electrons in space. And so if I have a carbon-carbon single bond, I'll have this sort of density of electrons in space. And if I add them all together, it'll be like the density of 2 electrons. If they have a double bond now between them, that density becomes greater. Now I have a greater density of electrons in space between them. But that density is still between those 2 carbon atoms. So in space, basically all I'm looking at is twice as much electron density as I had with a single bond. And then if there's a triple bond between them, then that's even higher density of electrons between those. Still in space, still between those carbon atoms, but now there's 3 times as much electron density. It's still a single group. And so we can imagine that this group with a triple bond has a lot more repulsive power than either a single bond or a double bond, because there's 3 times as many electrons in there. That density is much higher. It's going to repel other groups a lot more than a single bond would. So what we had to consider when we're dealing with these shapes is thinking about all the different kinds of areas of electron density there would be around an atom. And there's only two. There's only two things that there could be. A shared group of electrons, like we have with carbon-carbon, or if we have something like oxygen, which generally has two single bonds, so there's some density there, and there's some density there. It also has a pair of two lone pairs of electrons. So there'd be some density up here, and there'd be some density over there. And that's really the only source of electron density around atoms. Bonded electrons and lone pair electrons. That's it. And so basically we had to add together the lone pairs and the bonds, and then we could figure out how many areas of electron density there were around the central atom in a molecule, and that will give us the shape. And so there's a number of relatively, I say relatively, easy shapes. These are like the sort of basic groups of geometries there can be. There can be two areas of electron density around an atom. There can be 3, 4, 5, or 6. That's about it. And so these would be the basic geometry groups that molecules would find themselves in. And if you have a look at these different shapes, what you'll notice is that every time you look at a different geometric group, they place themselves as far away from the other electron groups as they possibly can. That reduces the electrons coming close to each other and repelling. And so the most stable form are these basic 5 geometric groups. We have linear, we have trigonal planar, or trigonal planar, however you want to pronounce it. Those things are basically 2-dimensional. So they're all in a plane. Then we get introduced to 3-dimensional shapes when we get to 4 regions of electron density. We have tetrahedral, when there's 4 groups around the central atom. When there's 5 groups, we have this shape here, which is basically 2 tenths on top of each other. With 5 groups, we have these 2 on the top. Remember, we called those axial, that are above and below. And then we have these 3 that go around the outside. We call those equatorial. They go around the middle. And then the last one with 6 different groups of electron density basically looks a lot like the trigonal pyramidal, except that we add another group around the middle. So now we have 2 axial and 4 around the middle, 4 equatorial. And this thing could basically be rotated in any direction and looks the same. They're all 90-degree angles to each other. The other thing we were introduced to was the idea of bond angles. And a bond angle is just the angle that 3 atoms make. So for instance, this atom, and this atom in the trigonal plane, there we go, 1, 2, 3. What is this angle? With the central atom being in the middle. And so we all have these different angles show up. Linear, we have 180 degrees. That makes sense. It's completely flat. It's 180 on this side, 180 on the lower side. That gives you the full 360. When you have a trigonal planar, there's 3 in a plane. So again, you have 360 degrees broken down into 3s, so that each of those bond angles is 120. It wasn't until we got to the tetrahedral we got this new sort of bond angle. And we'll remember, hopefully, that's 109.5. These are what's called ideal bond angles. And we learned that there will be some changes from ideal, and that is something we're going to have to recognize. All of this stuff you're not going to have to memorize. I gave you the nice summary. You remember the nice summary? That's on Canvas. I recommend you either print it or have it on your window on your computer or your phone when you're doing these sort of problems. But you don't have to memorize these things. I mean, I don't like to memorize things. Too old to memorize things. And we were then introduced to the idea of how do we figure out which one of these geometric groups does our molecule fit into. You remember the first thing we have to do is figure out what the shape looks like when we make a dot structure. So we'd make a dot structure like with water. We'd go, okay, oxygen has 6 electrons, hydrogen has 2. These two hydrogens have 2 together, so I need 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is what the dot structure of water looks like. Now I have to figure out what sort of geometric group this falls into, and I use the Axe body spray arrangement to figure it out. I have a formula here, and that's going to tell me which group it fits into. So A is just the central atom. Which one's the central atom? Oxygen. Okay, that's my central atom. How many atoms surround it? So I count them up. 1, 2. Okay, so I have A, X, 2. And how many lone pairs are around my central oxygen? I count those up. 1, 2. Oh, okay. So what I have is A, X2, E2. That means there's 4 groups around it. I add up the X2 and the E2. That tells me there's 4 groups around it. So I know what group that is going to be. That's going to be tetrahedral. But does that mean the molecule is going to be tetrahedral? Is the molecule tetrahedral?
No.
How come? How come we don't say that? How come we say the molecule isn't tetrahedral? You're right. You're absolutely right. Why don't we say the molecule is tetrahedral as well? Anybody want to help?
If it has lone pairs.
It has lone pairs, right? And do we consider the lone pairs when we're talking about the shape of the molecule itself?
I believe so.
Well, then you would say the molecule is tetrahedral, wouldn't you? The lone pairs are important for determining the shape. I don't want to say that they're not. They definitely are. The lone pairs tell us basically which geometric group that molecule fits in. But when it's time to say what shape the molecule is, and I want to make a distinction between the geometric group is one thing, and the molecular shape is another thing. So the lone pairs tell us I have AX2, E2 for water. So I add up X2 and E2, that's 4. So it tells me that is in the tetrahedral group, tetrahedral geometry. But what is the shape of the molecule? So I have some people saying, yes, it's tetrahedral, and some saying, no, it's not.
Would the shape be like bent or something like that?
Mm-hmm. But why do we say that is correct? Why do we say that the shape is bent and not tetrahedral?
Is it
Because-
because there's not like a actual bond? Like there's lone pairs instead of an actual bond?
Right. I mean, basically what it comes down to is that we can't see the lone pairs. That if we were to look with a variety of different methods at the actual shape of the molecule, we wouldn't see a tetrahedral shape. All we would see is this. We just see that. Because remember, electrons are so tiny. Electrons are super, super, super small. They have 1/4000th the mass of a proton or a neutron. They're incredibly small. So they're almost impossible to see directly. We can see the oxygens and hydrogens in a water molecule. We can actually detect them. We can see them in space. The oxygens, the electrons we can't really see. So when we look at the shape of water, we don't see the lone pairs. We know they're there because if they weren't there, the shape of water would be this. It'd be linear, but it's not. It's bent. And so we say it's bent because that's what we can actually see. But the group, the overall geometric group that molecule falls into, that is determined by the lone pairs. The shape that we can actually see, we can't see the lone pairs. So we say that the molecule's bent. And that's the difference. So I want you to be aware of that, because when you're taking a test or trying to explain it to somebody or thinking about it in your own brain, remember, as it says here on the slide, the electron group arrangement is defined by bonding groups and lone pairs, non-bonding groups. But the molecular shape is determined only by the three-dimensional arrangement of atoms, of nuclei, atoms. We can see nuclei, they're dense. We can see them in space. Electrons we can't see in space. So there's a difference between the geometry, which is 1, 2, 3, 4, 5, 6. What basic geometry is that? And then the actual shape itself, which is a subset inside the geometric group. And we'll have a look at what some of those are. Okay, let me clear those. So then this brings us back to the bond angle again. Again, this is between nuclei. So this is about a molecular shape. So we're looking at atoms in space, and what is the angle between 3 of those atoms, one being the central. And so we saw that when we had linear, it was 180. When we had a trigonal planar, it was 120. And then when we had a tetrahedral, it was 109. Those are all what we call ideal bond angles, where if the central atom is surrounded by exactly the same things, like for instance, methane, where we have a central carbon and 4 hydrogens around it, they're all identical. It's a completely symmetric molecule. Those would have the ideal bond angles of 109.5 degrees. But what if there's some asymmetry in there? What if they're not exactly the same all the way around? For instance, what if there's a double bond between the central atom and one of the surrounding atoms? That's going to change these bond angles, because you remember, as we mentioned at the beginning of my raving today, a single bond has a certain amount of electron density. A double bond is going to have twice as much electron density. And remember, since groups of electrons repel each other, this double bond here will repel the surrounding atoms a little bit more. It'll push them a little bit further away because there's more electron density. There's more negative charge. It's going to push them a little bit further away from ideal. If we have a different atom, like let's say we have a great big atom like iodine or something, some big atom, there's a whole lot of electrons in it. That's also going to push the other atoms a little bit further away because you have the big atom with lots and lots of electrons. And a lone pair will also push those other two atoms away, because basically a lone pair is just density of electrons in space with no nuclei there. It's basically like an uncapped group of electrons. So it's actually a lone pair pushes things away more than a double bond or a big atom, because there's no area of positive charge out there to sort of reduce that repulsion. So lone pairs repel quite a lot. So what you'll be expected to know is that when you make your dot structure and then you draw the basic shape, if you're asked what is the bond angles in between, you won't have to know exactly what they are, but you will have to know, are they more than ideal or are they less than ideal, depending on what's surrounding that central atom, okay? So let's look at some of these shapes. This is sort of where we left off the other day. So the very simplest shape is linear. And so there's no difference between the geometric group and the actual shape because they're both linear. There's just a straight line. So you have examples like carbon disulfide or carbon dioxide, where it's just a line. It's a line, because if we look at what our AX model, carbon is the central. It has 1, 2 atoms around it, and it has no lone pairs. And that's usually what carbon is like, right? When we're making these shapes, carbon almost always has 4 bonds and no lone pairs. So in this instance, AX2, that is linear. So the geometric group and the shape are the same. There's no subset of shapes. They're all linear here. And then when we get to 3, we see now there's 2 subgroups. There's actually 2 shapes in this particular geometry. Because when I have 3 electron groups around, 2 of them can be atoms and 1 of them can be a lone pair. Like for instance, sulfur trioxide. Sulfur has 3 oxygens around it and no lone pairs in this particular setup. So A is the sulfur, X are the 3 oxygens, and E is 0. There's no lone pairs on the sulfur. So the most stable way for that to form is to be on a plane with 120 degrees between each particular oxygen. Oxygen, sulfur, oxygen bonds are all the same. This is a completely symmetrical molecule. And because it's a completely symmetrical molecule, it's not going to make it polar or unpolar? No, unpolar. Non-polar.
Non-polar.
Why is that?
Because it's symmetric.
Right. What does that mean, though? Because it's symmetric. What makes something polar or what makes something non-polar?
If something's polar, it's pulling to a specific side.
What's pulling to a specific side?
Or it's electric negativity.
So it's slightly more negative on one side than the other.
Yes, that's
Okay.
what I would guess.
So if something's completely symmetrical, can you have a difference in electron density on one side or the other? If it's completely symmetrical in every way.
Yes.
Can you?
Yeah, I guess so. If
Okay.
there's partial charge differences between two sides, or
Well, then it wouldn't be symmetrical then, right? I mean,
what if the
that's the
linear?
definition of symmetrical, is that it's completely the same all the way around.
What if it's a linear, but the two different charges on the different side?
Ah, it's not symmetrical then, is it?
Oh, okay.
Yeah, no, you make a good point. I mean, like something like hydrogen cyanide or cyanic acid. That's linear. This is a linear molecule. But there's a lot more electrons on this side of the molecule than on this side. Notice there's a triple bond on the right and a lone pair on the nitrogen. There's a lot of electrons on the right side of the molecule and hardly any on the left. That is a polar molecule because it's not symmetrical. On the other hand, carbon dioxide, it has polar bonds, and we'll talk about this more in a minute. It has polar bonds. This carbon-oxygen bond is polar. Oxygen is more electronegative than carbon. It's pulling electrons away from carbon. But it's the same on one side and on the other side. I have oxygen on one side, I have oxygen on the other side. I can look at it from the top or from the bottom, and it's symmetrical. And so it's non-polar. So there's two different shapes when I have three electron groups. I can have three atoms, which are all identical, and that would give me a planar group and be completely symmetrical. Or I can have two different atoms and one lone pair, and then I get something that is bent. So this would look like water because I have that bent shape. But the group it's in is different because with water, I've got two lone pairs. In this particular instance, I only have one. But from looking from the outside, they both look bent. So these are some of the factors I mentioned before affecting lone pairs. And I mentioned affecting angles. And I did mention that lone pairs really repel other atoms because, like I said, you have this sort of basically free electrons in space with no nucleus around to sort of reduce that charge. So I have just two negative charges floating in space. That is going to repel other lone pairs and other electrons, other shared pairs of electrons or bonds away from it. Double bonds have more density, as I showed. You basically have twice as much electrons in a similar space. More density, more negative charge. It's going to push things away. So instead of having precisely 120 degrees, you can see here, those two hydrogens have been pushed, not a lot, just a little further away from the oxygen, making that angle a little more and making the angle between the HCH angle a little bit less. So you won't have to remember exactly, is it 120 degrees or it's exactly 116. You'll just have to remember that it's less. So your answer to the question is, what would you expect that bond angle to be? All you would have to say, I expect it to be less than 120. What would you expect this bond angle to be? You would just say, I expect it to be greater than 120. What it is exactly, no, that's you don't have to know that. Just know that it's either less than or greater than, okay? So we have three different shapes inside the tetrahedral geometry. So this, when I have 4 different things around a particular atom, well, it can either be 3 atoms, an electron pair, it can be 2 atoms and 2 electron pairs, or 4 atoms. So when it's 4 atoms, that means it's tetrahedral because there's no lone pairs in the middle. I can see each of these atoms in space. That is going to be a tetrahedral shape. When I have something with 3 atoms around it and a lone pair, remember, I can't see the lone pair. It's help determining the shape, but you can't see it. And so it looks like you have trigonal again because there's 3 atoms around it. But this time it's not flat. It's not planar. It's a pyramid shape. It's going to be bent. Basically, it looks like it's bent, but with 3 atoms rather than 2. So we call that trigonal pyramidal. Then when we have 2 atoms and 2 electron groups, like water, then we get the V shape or the bent structure again, okay? Now, again, don't have to memorize any of these. What I want you to know is how the whole Axe body spray formula works. How many atoms are around the central molecule, how many lone pairs are around the molecule. You add those together to figure out which geometry it fits into, and then look and see which shape it is. Does it have 1 electron group? Does it have no electron groups? Does it have 2 electron groups? That will tell you the exact shape of the molecule rather than the geometry, okay? Remember, geometry is general and shape is specific for that molecule. Then when we sort of get some weird shapes when we get into like 5 and 6 groups around the atom. When we have all 5 taken up by atoms, we have trigonal bipyramidal. So again, we sort of have 3 around the outside and 2 what we call axial positions. And so this is a geometric shape where you have 3 around the outside and 2 up and down. And so we call that trigonal bipyramidal. When we add a lone pair, we get this cute shape called a seesaw. So we have 2 atoms that are sort of linear, and then the other 2 sort of are bent. We call that a seesaw shape, basically with the lone pair being some kid sitting in the middle of the seesaw who isn't moving while the other 2 go up and down. Then if we have 2 lone pairs, look and remember that the lone pairs go into the equatorial positions. The equatorial positions are around the outside, not up and down axial positions. Anyone remember why the lone pairs get put into the equatorial positions? Why do they get put there? What's the difference between the axial positions on the top and the equatorial positions around the middle?
The angle?
The angle, that's right. So what's the angle between the groups around the middle, around the equatorial region?
120.
Mm-hmm. So if they're 120 degrees apart, that means they're further spaced. There's more distance between them. And so if you have something that repels greatly, like a lone pair, that will get put into the equatorial positions because that gives you the maximum distance between the that lone pair and either other atoms or other lone pairs. So with the seesaw shape, we have 1 group of electrons in the equatorial position. With the T shape we have here, we have 2 of them. 1, 2 put into the equatorial position. And then finally, when we have the linear shape, we've got 1, 2, 3 groups of lone pairs, all in the equatorial position. That gives you the maximum distance between the lone pairs and other surrounding groups, be they other lone pairs or other atoms. Because if we put them here, that would give us a 90-degree angle between that lone pair and the other groups around it. And that would present too much, that gets the electron groups too close to each other. We get too much repulsion. By putting them in the equatorial position, that gives us greater distance and less repulsion. And remember, all of these shapes are all about reducing the amount of electron repulsion to the lowest amount you can possibly get. And that means putting the lone pairs in the middle, not on the top or the bottom. So just as you just pointed out, there's 90-degree angles between the axial and the equatorial. So what you're going to want to put on the axial is something that's not going to repel everything. And so what you'll do is you'll put atoms here. You'll put an atom here and an atom there, because atoms repel the least of all the different single bonds, repel the least of anything. So that's where you want to put those, because basically you're ensuring that there's only going to be 90-degree angles between whatever you put here and whatever you put here. So you want to make sure those are that have the least repulsive quality. The ones with the highest repulsive quality, great big atoms or lone pairs, you want to put those in the equatorial positions. Those have 120 degrees from each other. Excuse me. So that's where you're going to want to put groups that have a lot of repulsive capacity, like a lone pair. When we get to the final, we get to six, we get what's called an octahedral shape. And so if I have all atoms, this is going to be completely symmetrical and every bond is 90 degrees. And here's some examples where you have a central, basically you see like things like sulfur and iodine, things that can like have a large number of electrons and can basically violate the octet rule a lot. And so sulfur is one that goes in there fairly frequently to make 6 bonds because it has 6 valence electrons. So when it's all atoms, we get the classic octahedral shape. When there's one atom, when there's one lone pair, you get this weird shape where it looks, you have 90-degree angles. So you have these 4 that are in a plane basically around the outside, and you basically now just have one axial atom. The other one is your lone pair of electrons. Then when I have 2 lone pairs of electrons, I basically put them on the top and the bottom to be as far away from each other as they possibly can, with atoms around the middle. And this looks like a square plane. So rather than having a trigonal planar, we have a square planar this time because we have 1, 2, 3, 4 atoms in a plane surrounding the central molecule, the central atom in the molecule. Okay. So how can we have these weird shapes? Remember, we don't get these weird shapes until we get to period 3. Why? What's different about period 2 and then period 3 and 4 and above? Like period 2, I've got all the classic thing. I've got oxygen, I've got nitrogen, I've got carbon,
elements in period 3 have a D shell?
And what does that do for them?
Means they can have more valence electrons, right?
Yeah, it means they have more place to hide electrons. So carbon, or this oxygen, has 6 valence electrons. Sulfur, right below it, has 6 valence electrons. Sulfur looks like oxygen, but oxygen only has 2 places to put electrons because it only has 2 shells. So in the second shell, it's got S and P. And we know that S takes 2 electrons and P takes 6. So it's only got those 2 shells. So the maximum number of electrons it can have in that second shell, in its valence shell, remember the valence shell is the one furthest away, is 8. It can't have any more total electrons than that while having its 6 valence electrons. Sulfur, on the other hand, has that D orbital that you mentioned. D orbital could handle 10 more electrons. And so sulfur still has 6 valence electrons that it calls mine. But the total number of electrons that can be involved in bonding can be more than 6. It can have 12. So it can make 3 double bonds. And that's fine with carbon. That's a total of 12 electrons because there's 6 bonds. But it keeps 6 of them for itself in determining its charge. So it has its 6 valence electrons, it's chill. But the total number of electrons surrounding sulfur can be more than 6. So it can form more than 4 bonds. So here's just the summary. So this is what's printed out, It's what's made available to you on Canvas. So what I want you to sort of the take homes, what I want you to remember is when you do the AXE, remember that the total number, X plus E, gives you the total number of electron groups. That will refer you to this geometry, or this geometry. It's the actual breakdown of what is X and what is E gives you the shape. So when, if X plus E gives you 3, if there's just X's, if there's just atoms, that gives you that particular shape. If one of the groups is an electron, is a lone pair of electrons, that gives you that particular shape. They both fall, and this is, I can't hammer this enough. They both fall in this overall geometry, but there's a difference between geometry and shape. Geometry tells you how both the atoms and the lone pairs are arranged in space. The shape just tells you the atoms, okay? So remember the difference between them. And then finally, you won't have to memorize these bond angles either, but remember when they're going to be less than 109, when they're going to be less than ideal, and when they're going to be more than ideal, depending on which atoms I'm asking you gives which bond angle I'm asking for. If it's the bond angle that's being pushed, if their atoms are being pushed together by a lone pair, that angle is going to be less.
If you have a molecule
Oh, go ahead.
and double and triple bonds and a single bond, how can you determine the less than ideal or more than ideal?
Know what that would be. Something with 6. So yeah, you would look at what are the 3. So yeah, I don't know if there's anything like that, but there's something with a triple, a double, and a single bond. I guess it's theoretically possible. I just can't think of what it would be. You're wondering what that bond angle would be. Yeah, you would. The triple bond would push the double and the single away from it. So basically, the bond angle. So if I had something like this, so B, C, D. If I had something like that, this triple bond would push the double and the single away, so that DAC, the bond angle DAC, would be less than 120 degrees, and the bond angle BAC would be greater. So yeah, because wherever there's more electron density, that pushes things away from it. Wherever there's less electron density, that gets pushed together. So yeah, whatever the triple bond is, would be pushing the other two away from it. Is that what was that the sort of shape you were thinking about?
Yes, thank you.
Damn, now I want to find out if that thing exists. I'm going to look and see if there's a molecule that has a triple, a double, and a single. Because if it could, that would be cool. I'm going to look that up. That's why it's fun teaching. I never think of these crazy ideas. And then someone will come along, well, how come you can't have that? You're like, gee, I don't know. Maybe you can. I'll get back to you and see if there is such a crazy molecule. So that would be very unstable, I would think. So something like that would probably blow up real good. So now I would definitely want to find out what it could be. And so then when we have 5 and 6 groups, what I want you to take home is what those bond angles basically are going to be. And remember that lone pairs get put on the outside where they can do the least amount of repulsion. So
Excuse me.
yeah.
So for AX3E2, why wouldn't the lone pairs be like in the axial so they can have 180 degrees?
So they wouldn't have 180 degrees. They'd be greater than 120 between the two of them, but it wouldn't have 180 degrees.
I mean,
AX2E2, which one are you talking about?
AX3E2.
Right, T shape. Okay.
Why wouldn't the lone pairs go to the axial instead of equatorial, like here and here, like having 180 instead of 120?
Well, because then you would have the bond angles between if we had this with a lone pair at the top and a lone pair at the bottom and the 3 atoms, that would give you the greatest amount of electron repulsion, because then all of the atoms would be separated by 90 degrees away from the lone pair rather than 120. So that would give you more repulsion. With this setup, one of the atoms has a greater distance away from the lone pairs and reduces the amount.
It's not a bond angle of the lone pairs themselves. The bond angle of the lone pair and the
atoms. Yeah. 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 So remember that the angles on the outside of the equatorial are 120, ideally, and the axial is 90. So we have 90 degrees there, and then around the outside is 120. And then remember that depending on what's out there, that can change those bond angles. Okay, so
Excuse me, sir.
Yes.
How do we describe the shape, geometry shape of AX6?
Octahedral.
Okay.
Yep, it's because both we can
No, I
see
mean
we can
geometry.
see all of these atoms. So in this instance, the shape and the shape and the group, the geometry is the same. Same with when there's 5. The group, trigonal bipyramidal, is the group, and trigonal bipyramidal is the shape, because they're all atoms. We can see all the atoms. That's true for linear, for trigonal, planar, and for tetrahedral. The shape and the geometric group are the same if it's all atoms surrounding it. It's only when we introduce lone pairs does the shape change. The shape is now different from the geometry. Okay?
They're not what they seem.
Thank you.
One moment they
Hello. All right. So what do we? So this takes us. Let's actually do some of these things. That's more fun. So this is what we do when we have a molecule and we want to draw the shape. First thing we do is the Lewis structure, the Lewis dot structure. Without the Lewis dot structure, we cannot draw a shape, because without the Lewis dot structure, we don't know how many lone pairs and atoms there are. We know how many atoms there are going to be around the central atom, but we won't know how many lone pairs there are. And so we'll be able to figure out what geometric group it's in, but we won't know what shape it is until we know where all the lone pairs are. So basically, we note any positions of lone pairs and double bonds. Also, we need to know where there's a double bond, where there's a triple bond, where there's a lone pair. Then we count all the bonding and non-bonding groups with our Axe body spray formula, and that will tell us what the shape is. Once we have the shape, then we can sort of figure out what the bond angles are as well. Those two should actually be flipped. We figure out what the shape is, then we figure out what the bond angles are. So let's do a couple. So what would I call this molecule?
Phosphorus fluoride?
Close.
Wait. Phosphorus trifluoride.
There you go. Yeah, phosphorus is not a metal. And so since it's this is not an ionic compound, we'd have to say exactly how many fluorine, because it could be 2, it could be 3, it could be 5. So PF3. So let's draw it, shall we? So who goes in the middle?
P.
Phosphorus, for a couple of reasons. One, there's only one of it, so probably a pretty good idea that goes in the middle. 2, it's less electronegative than fluorine, because everything's less electronegative than fluorine. And 3, how many bonds can fluorine make?
1.
Just 1. How many bonds can phosphorus make?
3 or 5.
We can make 5, because it's in the third. It's not in the second group. It's in the third group. Sorry, period. And so it has more places to put bonding electrons. So let's put phosphorus in the middle, and we'll put 1, 2, 3 fluorines around it with 1, 2, 3 bonds. So let's count up our total electrons. How many valence electrons in phosphorus?
5.
Okay, and then how many in fluorine?
7.
So 21. So that's 26 total electrons. I've got 6 in bonds, remember? 1, 2, 3, 4, 5, 6. So I need 20 electrons. Now, when I have a whole bunch of electrons, where do I put them? Do I start in the middle or do I start on the outside? Do I put the electrons in the middle of the molecule first, or do I put them on the outside of the molecule first?
On the outside?
Yeah, put them on the outside. How many do I give each on the outside, though?
6 for each.
Why 6?
Oh, I mean 3 pairs of long pairs.
Mm-hmm. But why 6 of them?
Because there is already a bonded electrons.
Right, so you would want to give an octet. If they're not hydrogens, they're going to need an octet. Hydrogen only needs 2 electrons to fill its first shell. Everybody else, with a couple of exceptions, needs to fill an octet. And so fluorines have 7 valence electrons, and they want 1 more for an octet. So I'm going to put 6, as you mentioned, on each fluorine, 3 lone pairs. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 18. Now I have 2 electrons left over. Where do they go? I got 2 electrons left. Where do I put them? Right, changed your mind. Where do I put the lone pair? I got 2 left. Do I make another bond? What do I do with them?
Just put it in the middle.
Put them in the middle. Yeah, whenever you have electrons left over. When everyone on the outside has a full octet, that means you can't make any more bonds with those atoms. They're happy. They have a full octet. But look in the middle. Because if we look in the middle, how many valence electrons is phosphorus supposed to have? It's supposed to have 5. How many valence electrons does it have in this particular molecule? Valence electrons. So in this particular model, how many valence electrons does phosphorus have?
Five.
Where do you get them?
2 from the lone pairs and 1 each from the bond.
Excellent. That is right. Yeah, remember, when we're talking valence electrons only, we talk about valence electrons when we want to talk about what's the charge, what's the formal charge on each of these atoms. So we count. So those are what I call the mine electrons. So all the lone pairs that phosphorus has are mine. So that's 2. And it gets to claim 1 electron from each of these bonds. So 1, 2, 3, and then 2 for the lone pair. That's a total of 5. So it's not charged. Total electrons, remember, it gets to count all the shared electrons and the lone pair. Because that's the whole point of sharing electrons, is that I can have an octet, you can have an octet, everybody has an octet. So phosphorus for total electrons, 6 for the 3 bonds, and 2 for the lone pair for a total of 8. So fluorines, all the fluorines have 8, phosphorus has 8. Everybody's chill. So what shape is this going to be? So when I do what is my Axe body spray formula for this? I've got my A, X, E. So my central atom is the phosphorus. So how many what's my X? What's my surrounding atoms? How many?
3,
3. And then how many lone pairs?
1.
1. So which geometric group does this go into when I have X3E1?
4.
4. And that is which one? Do you remember?
Tetrahedral.
That's tetrahedral, exactly. So the group that it's going to be in is tetrahedral. Is the shape going to be tetrahedral? Is the shape also going to be tetrahedral?
No.
No. Right, because they're not all atoms. If they were all atoms, that would be a tetrahedral shape. It's a tetrahedral geometry, but it's not a tetrahedral shape. So what shape is it?
Trigonal pyramidal.
Right. Yeah, it would look similar to ammonia. Ammonia is the classic trigonal pyramidal because it has a lone pair. The nitrogen is lone pair and three bonds, just like the phosphorus does, because phosphorus is 1 below nitrogen. So it forms similar shaped compounds. It has a lone pair and 3 bonds. So if ammonia is trigonal pyramidal, so is this particular shape. So let's have a look and see how we did. Oh, we forgot to do the bond angles. Yeah, so it's a tetrahedral arrangement, but the shape of it isn't. The shape is going to be the trigonal pyramidal. And we could probably, hopefully we would have remembered that the bond angle between those 3 fluorines is going to be less than ideal. It's going to be less than 120 degrees, or less than 109, sorry, less than 109. Because we have a lone pair up here. And those fluorines have a lot of electrons too. So that lone pair is going to be pushing those fluorines away from the lone pair. And this angle is going to be less than 109.5. All right, that's fun. Let's do another one. The other one was...
So I have a
go
question.
ahead. Yep.
So you mentioned the naming. So how do you name ICl4 minus?
How do we name it?
How do you name that ion?
Oh, I can't remember.
Because I in one of the recitation.
Oh yeah, they come up with the name of it. I think they come up with the shape of it.
Name. I think it was name.
Was naming it too?
Yeah.
Yeah,
I think
it's a
it was-
shape.
I think it's a shape.
Just the shape. You could look up the name. I can't remember the name offhand.
I looked it up and I didn't find it.
Oh, interesting. Okay. I'll try and find a name for you. Where's my... Because yeah, it is a molecule. So that's ICl4 minus?
Yeah.
Okay. But you should have the shape, right?
Tetrachloroiodate ion.
Something like that. All right, so
Ferris said
tetrachloroiodate, that makes sense. I mean, you look that up, Ferris? Yeah, it was online. Yeah. I mean, that makes sense what it would be. Interestingly, that's a nonpolar molecule, right? Which is weird, thinking that something that's charged is nonpolar, but it is. So this is going to be how this particular, so in this instance, the carbon is going to be the central atom, okay? Which makes sense because in this instance, carbon has the lowest electronegativity of both oxygen and chlorine are both fairly high in electronegativity. So in this instance, carbon is going to go in the middle, and I'm going to have oxygen, chlorine, chlorine. Okay, with 1, 2, 3 bonds. All right, so how many total valence electrons is this molecule going to have? So I got carbon, I've got oxygen, and I've got chlorine. So how many on carbon? Valence electrons.
4.
4, right. It's in group 4, 4 valence electrons. Oxygen?
6.
6. And chlorine?
Total of 14, but
Yeah.
in group 7.
2 times 7, right. It's in the last group next to the noble gases. It's in group 7. It will have 7 valence electrons. So let's add them all up. So 14 plus 6 plus 4, that's 24 electrons. And I've got 6 in bonds, so that leaves me with 18, right? 18 electrons? Yeah. So 18 electrons left to go. So as we mentioned last time, we have 18. Let's put them around the outside. So 1, 2, 3, 4, 5, 6. I want to give everybody an octet so they're happy. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm done. I don't have any electrons left. So the chlorine has an octet. The other chlorine has an octet. The oxygen is an octet. That should be good. But now so they all have an octet. It's time to look in the middle and see if our central atom has an octet. Does the central atom have an octet?
No.
No, it doesn't. It only, how many total electrons does the carbon have?
6.
It only has 6. So that's a problem. And so we deal with that. So that's going to be an issue. So now we have to decide one of those surrounding atoms is going to have to donate a pair of electrons to satisfy the octet for the carbon. But the question is, which one is it going to be? And so when you want to figure that out, the best way to do that is to figure out
Oxygen.
what is the formal charge on them. Okay, so what is the formal charge on the chlorine here? How many valence electrons should chlorine have? And how many valence electrons does chlorine have? So chlorine is supposed to have 7. How many valence electrons does it have in this model?
7.
It has 7, right? It's got 2, 4, 6, and this, and one of these from the bond. So it has 7. So there's no charge in this chlorine. So there's no charge in this chlorine because they're identical. What about the oxygen? How many valence electrons should oxygen have?
It has 7, but it's supposed to have 6.
Right. Oxygen is supposed to have 6 valence electrons. It's in group 6. So we say it has 6 valence electrons. It's supposed to have 6. It actually has 7 here. It's got 2, because it looks like the chlorines, right? It has 2, 4, 6, and 1 from the bond. When we break it in half, that's 7. So its charge is -1. Uh-oh. Its charge is -1. What's the formal charge on the carbon? How many valence electrons should carbon have?
Four.
Should have 4. So carbon should have 4 valence electrons. How many does it actually have in this picture?
Only 3.
It's only got 3, right? It's got 1, that one from that bond, and that one from that bond. So it is 1, 2, 3. So the charge in the carbon is +1. This is an unstable situation. I've got a central atom with a positive charge, and I've got one of the peripheral atoms with a negative charge. Well, that's not stable. So what's going to happen when I have electrons around a negative charge and there's a positive charge next to it? Negative things like to go towards positive. One of these lone pairs is going to move to the middle and be shared with the carbon, forming another bond. So this lone pair goes away. Now I have a lone pair. I have one less lone pair on the oxygen that's now a double bond. So what's going to be the formal charge on the oxygen and the carbon? How many valence electrons does the oxygen have?
6.
Yes, I can hear you, Raymond. How many valence electrons does the carbon have? Anyone? Oops.
4.
So what are you counting? Here's my double bond.
I'm counting the ones from the double bond only has 2. And then
So it's got
the
2.
single bonds have 1.
I'm not talking. Oh, you're talking about the carbon.
Oh yeah, I thought you were
Yes,
asking.
yes. The carbon has 4 now. Right. The carbon has 4. So 1, 2, 3, 4. It has 4 bonds, and it gets to keep one of those electrons from each one. So now it has 4. So it's not positively charged anymore. It has no charge. What about the oxygen? How many valence electrons does the oxygen have now?
6.
That's right. It has 2 lone pairs, so it's got 2, 4 valence electrons, and it has 2 more, 5, 6, 1 from each bond. So it has a total of 6. So now it is no longer negatively charged, it's neutral as well. This is more stable. There's no charges, there's no formal charges at all. So we've reduced the formal charges from +1 and -1 to 0. Now there's no formal charges. And we're left with this structure. So the question is, what is this? What shape is it? What is this overall shape? So what shape do we have here? Carbon is the central atom. So what's my X and what's my E? How many atoms surround the carbon?
Trigonal planar.
Not the question. How many atoms surround the carbon?
3
And how many lone pairs?
atoms surround.
And how many lone pairs does the carbon have?
No.
None. So we don't have an E at all. So it's just AX3. So we look at our table, and what's AX3? AX3 is trigonal planar. Both the geometric group, the geometry, and the shape, they're both the same because there's no lone pairs. So if it's AX4, it's tetrahedral. If it's AX2, it's linear. There's no, the geometry and the shape are the same when there's no lone pairs. So we say it's trigonal planar or trigonal planar, wherever you're from. So the other question is, What is this bond angle? The chlorine, carbon, chlorine bond angle, this one right here. What is it? What should it be if it's trigonal planar, and what is it actually? So what's the bond angle? What's the ideal bond angle for trigonal planar?
120 degrees.
That's right. So if everything was cool and groovy in a perfect world, it would be 120 degrees. What's this bond angle though?
Has to be less because the oxygen pushes the chlorines closer together.
The oxygen?
The
You're right. It is less than 120
More
degrees.
electronegative.
But is it the oxygen that's doing that?
Oh, it's the double bond.
Yeah, there you go. Because remember, we're not looking at the atom itself. We're looking at the distribution of electrons. So remember, there's more electrons in this area of space than there is here or here. There's twice as much electrons in that region of space. So
But
that region of
chlorine
space
is bigger?
pushing it away. What?
but the chlorine is bigger.
Chlorine's bigger than what?
So you said if a bigger atoms comes in to the it would
Yeah,
push-
that can affect. Yeah, if we had like a really big atom and like 2 hydrogens or something, that will make a small change. This will make the double bonds and lone pairs have a much greater effect. So yes, it would be less than 120 degrees. So let's see if we are correct on this one. Excellent. Yes, it's trigonal planar. And our chlorine, carbon, chlorine bond is going to be less than 120. You can see actually quite a lot less than 120, 111. So that double bond makes a big difference in pushing those 2 chlorines together. All right, so I'm going to leave it there, and we'll the next time we get together, we'll look more at 5 and 6 electron shapes, and then we're going to move into chapter 5. So for my group this afternoon, we're going to be reviewing for the lab test. So I want you to come prepared with questions. I'm sort of just going to go over the sort of like the general things we learned from each lab, and we can review the pre-lab questions and the post-lab questions, as well as what things we should know about each lab. But come prepared with lots of questions, because I don't want to blather like I have this morning. So any questions about either that or what we've gone over this morning with shapes, or the test on Thursday, or anything? The Electoral College, anything you want to talk about? So everyone's cool with coming this afternoon. Hopefully, so if there's questions you have about the labs, pre-lab and post-lab questions, those are going to be important, because some of those may show up on an exam. So,
Excuse me, Professor.
yes.
I didn't get a chance to double check, but are all of our labs graded and up to date for the ones that are going to be on the exam, or are you still working?
1 through 4 are done, and I'm
Okay.
doing. So the test will be on 1 through 6. The last one we're not gonna do, because we just did it. So
Okay.
yeah, it'll be 1 through 6. Yes, if you have any questions about 5 and 6, because you haven't seen the grades yet, yeah, this afternoon would be a perfect time to ask about it. Anybody else?
I kind of have a general question about.
I love general questions.
Okay, so for my lab, one of your notes was the conclusion.
Mhm.
I'm kind of confused, I guess, still on conclusion. I guess I'm not doing it right. So I'm just saying what I learned in the lab, or is there something?
Yeah, what did you find out? I mean, what was the overall result? What do you expected it? If it was, why? If it wasn't, why? And yeah, basically, yeah. What was the take-home lesson from the lab?
Okay,
You know.
and also like kind of putting the my data into words, is that another way to kind of add to the conclusion?
Yeah, exactly. Yeah, exactly. That's basically what we're talking about. Your results section is, yeah, it's all very data oriented. It's got like lines and charts and graphs. In the conclusion, yeah, basically just sum up, you know, what are all these numbers telling us? Yeah, that's precisely what that should be. That's a
Okay.
good way of putting it.
What's the
Yeah.
name of this compound?
I don't know, dichloroacetone, maybe? I'm not sure.
Okay.
No, not acetone. Dichloroaldehyde. Something like that? Yeah. I can't remember. You can look it up. Anyway, any other questions? Okay, so I will see my group at 1:10. Everybody else, I'll be posting the test on Thursday at 9. And then you'll have 3 hours plus 10 minutes to finish it and submit it. And then in the afternoon, I was thinking either we would just like take the afternoon off and let our brains relax, or we could have a meeting and sort of we could go over what other recitation questions. Instead of doing a new recitation, we could just sort of just review what recitations you haven't submitted yet, what questions you may have about them, and we could work through some of the recitation questions that are harder to do. I haven't decided. Send me your suggestions, either an email, or what I'll do is I'll put a question on Canvas, and you can basically answer what you'd rather do. Okay, because it's all about you people. It is. Okay. Anyway, I'll see.
I have a non-related question, but what
Okay.
causes like chemicals to explode when you mix them together?
Oh, what causes explosions? Lots of cool stuff explodes. Things, well, what we've been learning about, these are shapes of molecules that form these shapes because they want to reduce the amount of stress inside the molecule. They want to basically form a shape that reduces the amount of electrons, running into each other and get a very low energy state. Some molecules, which they're difficult to make, are basically in such a shape that there's a lot of strain. There's an incredible amount of strain. Then they're sort of barely holding these things together. And if they were to come apart, the products are a lot more stable than the reactant. So you see a big difference between the energy of the product, of the reactant, which is a very, very high energy, and the products, which are very, very low. Typically, things that if like oxygen can be released, or nitrogen can be released, or water can be released, things like that, you will see like a very sudden and violent reaction with these sort of molecules, and they'll just release all that energy and violently, and you'll get an explosion. So those are the sorts of molecules that explode. Ones that are really, really unstable, have a lot of atoms that are like way too close together, and basically are made of atoms that are much more stable in other situations. Like the classic example, like nitrogen. Things that can release nitrogen are pretty explosive. So generally, that's sort of what they are. They're very unstable molecules that would be more stable if they weren't molecules anymore. When they form more simple molecules.
Because they want to separate so bad, they release a lot of energy in the process of doing
Yeah,
so.
exactly. Yeah, so we're gonna, when we do thermo, we'll be doing some thermochemistry, and that's the perfect time. I'll actually pick some of those molecules. That's a great suggestion. I'll pick some of these molecules that are really unstable, and show you that there's a lot of energy in that molecule, and then when it breaks down, that energy is much less. And so we look at the difference in the energy of the reactant and the products. And when there's a huge difference, you generally see explosions. The bigger the difference, the more violent that reaction is going to be. Yeah, I'm going to write that down. It's a great suggestion. So look at so with thermo, yeah, look at some, you're going to get to that fairly soon. I think that's chapter 6 or 7. So we'll deal with that very thing. And I'll put some cool videos up to watch things explode.
Okay, thank you.
Okay, no problem. All right. See some, if not most, this afternoon, and the rest. Good. Remember, I have office hours tomorrow at 11. So if you're like, panicking about, the test or whatever, you need some questions straightened out, that's what we're there for. So I'll be there from 11 to however long is required. Okay. So I'll see you then.